Okay, I'll make a start. So on Monday, we looked at our first way of controlling infectious diseases using vaccinations. We looked a little bit about the history of vaccination and how we can incorporate them into a relatively simple SIR model and seeing how that affected the overall number of infectious cases and how we could vary the vaccination rate, either if we're doing pediatric vaccination, so childhood, or if we're doing targeted vaccination for, say, a risk-structured model. And we saw that we would get a threshold proportion of the population that we have to vaccinate. And this is our vaccination threshold. And it also corresponds to our herd immunity threshold. So just to clarify as well, the idea of herd immunity is not that no one is going to be infected and that everyone's going to be protected. It's basically saying that we're not going to get an outbreak. So your R number, we think about either our R naught, or more correctly, it should be our effective reproduction number because individuals are immune. That number is less than 1. So even if we get a small outbreak, it's, because these are deterministic models, so things would just exponentially decay. In the real world, things are noisy and stochastic, and they're not exactly matched like these perfect idealistic models. You might get a small outbreak, but it's never going to take off and sweep through the population. It will maybe increase a little bit and then decrease or just decrease. Okay. So one of the misconceptions about herd immunity is that everyone is protected. It's not. It basically just means that the number of cases cannot grow deterministically. Okay. Okay. So today we are looking at non-pharmaceutical interventions. So I included this lecture because we've all had to experience a lot of non-pharmaceutical interventions. I am currently wearing a mask right now because I don't want to infect you guys with the cold I have. There are different types of NPIs. We're going to talk about some of those today, and concept of disease suppression as well. And then think about how we can modify our models to include these NPIs and look at their effects, and think about how strong they need to be in order for us to control or mitigate the effects of infectious disease sweeping through a population. Okay, so that's basically that intro slide there. The first thing I want to do is to have you guys brainstorm some examples of NPIs. So can anyone give me some examples of NPIs? There's literally one right in front of you right now, so no one has an excuse not to answer this one. Masks. Masks, yes. So masking is one example. What else? Social distancing, good. What else? Other examples of NPIs?
It was the disease.
Exactly, any disease. So yeah. Quarantining, yeah. So quarantining or isolating. How do you know who to put into quarantine?
Be tested.
Yeah, so some sort of diagnostic testing. Diagnostic testing on its own is not going to control infectious disease, right? If you just test people and then they just carry on with whatever they were doing, but it does help you target your interventions potentially. Anything else?
For some diseases that are like HIV, there are some medication that prevents people from being contagious.
That is true, but we are focusing on non-pharmaceutical. So nothing drug related. But on the thinking about HIV, think about how HIV can be transmitted. What non-pharmaceutical interventions might there be?
Being hygienic.
So hygiene is a general thing, yeah, even like hand washing, things like influenza. I'm just going to close that door. Any others?
Moving events online.
Yeah. So that in sort of social distancing, but more broadly, we saw lockdowns, right, as a more extreme form of social distancing. What else? I'm going to go back to HIV as an example, or gonorrhea, chlamydia. Condoms. Thank you. Yeah. You could argue things like abstinence as well could technically be included in here, but there's a lot of judgment related to that, so I'm not going to include that here. How about things like your ability to go to a different country during the pandemic? Yep, so travel restrictions. Interesting music coming through here. Okay, so there are lots of different ways in which we can intervene that don't include any sort of drug or vaccine interventions, okay? So let's think about what these kind of things look like in an SIR model. Okay, so again, we're thinking about proportions here. And I'm not going to include any demography. So our standard SIR model, we have our transmission term, minus beta SI coming out of our susceptible class. Our infected class, we're going to have beta SI, so those infections, minus gamma I. For simplicity here, I'm not going to assume that there's any disease-associated mortality. These are just individuals who recover. So while we're not talking at all about models with disease-associated mortality, functionally, they do change things, especially from the host perspective. They complicate matters because of changing population sizes. Potentially, you can counter that by adjusting the births to account for those deaths as well, so things remain constant. From an infections perspective, though, an important thing to remember is whether an individual recovers or whether they die, that's essentially a dead end, okay? So functionally, those often operate as very similar things or having similar effects. It's worth bearing that in mind, that mortality and recovery are essentially the same things as far as pathogen is concerned, at least for that particular infection. Okay, will affect population sizes, you know, the proportion that's susceptible, say, but from an individual infection, once an individual recovers or dies, that's basically the same thing. Okay, so this is our basic SIR model without demography. How could you modify this to include NPIs? In a very straightforward way, without, say, even adding additional equations in all classes. Like, what terms would you modify, and what would those modifications correspond to in terms of the types of NPIs we've just discussed? Okay, so this is one example. So we've got these betas here, and remind me, what does that represent?
How likely infected class will infect the society.
Yeah. So remember, we had that this term here was essentially, depending on your type of transmission, here we're assuming density-dependent transmission, that this was really some contact rate, let's call it C, times by the probability of transmissions per contact, if we've got density-dependent transmission. Okay, so we could even think about how our NPIs might differentially affect, say, the C or the P, right? So the contact rate or the probability of transmission. So let's think about some of these NPIs above. So let's take masking, for example. It's going to affect your transmission rate. How's it going to do that? Which terms are going to affect here?
We should calculate, like, you should have the percentages that is being started because of the mask.
It brings down the, sorry?
Like the percentage of the people who are more like
So in terms of these different parameters
it
here.
would be like better one some number that it is the proportion of the
Okay.
that we wearing mask brings down the con.
Okay, so if I've set this transmission rate beta to equal the contact rate times by the probability of transmission per contact, and then I said, say, wearing a mask or mask wearing in general is reducing this by 50%, what would I do to this?
No, divided by
Divided by 2, yes. So if I said the transmission rate has been halved because of mask wearing, I'll be dividing this by 2. Another way of looking at this is I would be modifying this p term. So say replacing it with p tilde, which is p over 2. Or if I said that it was reducing, let's call it 1 minus r here, where r is the strength of the effects of mask wearing when there's no masking and r is equal to 0. There's no effect on this probability of transmission. When everyone is wearing masks and masks are 100% effective, this would reduce the probability of transmission to 0. Okay. How about social distancing? What term would that affect? What parameter would that affect? Yes, C. So this is an example of social distancing would affect C. You could have a similar thing here, right? It could say if you had a strength of social distancing going between 0 and 1. So 0 is no change, 1 is everyone staying at home and not coming into contact with anyone. Reduces that contact rate. Okay, so it's useful thinking about the ways in which those NPIs affect the different components that go within into this model. Let's pick a different one. Let's think about what happens if we have, say, diagnostic testing and some quarantining or isolation. How does that affect this model? It won't affect beta because that's just transmission between an individual that's moving around. This one's a little bit trickier than the other one, but what's the other term that it could affect? That would affect your change in the rate at which new infections are, or the rate at which the infections grow, I should say. This one? Gamma. Yeah. Okay, so it effectively changes this gamma. That's the other way in which we could use non-pharmaceutical interventions to affect the rate at which this class grows. It could affect it. I mean, another way of looking at this is to think about subtracting, I'll call it tau for testing. Tau times by I, and those individuals maybe go into another class. Let's call it a quarantining class. So by removing individuals at a faster rate from this infectious class, they're still infected, but they're not infectious. So think about before when we had also our SEIR model, where individuals were infected, but could be either exposed and not yet infectious, or they're infected and infectious, so they're able to infect other people's. In a similar way here, we had individuals who are infected and infectious, and here maybe they are not infectious because they're staying at home, or that they're less infectious because they're less likely to come into contact with people because they're quarantining. So this would be another way of reducing the growth rate of the epidemic is by testing and then isolating or quarantining those individuals. Okay, so basically these are the two main ways in which we're going to be, well, you can think of it as 3 ways in which you're affecting epidemic growth. Either by reducing the contact rate, reducing the probability of transmission per contact, and both of those things function the same way essentially in reducing beta, or doing something to this removal rate from this infectious class. Sorry, the question.
So how would any people from DQ transfer to DR, or would they just...
Yeah, you could have some flow from here to here as well. Yeah. That was just to illustrate that they're being taken out of that class, but yes, you could move them into this class as well. Okay, so we can see that we can do some relatively straightforward modifications to our SIR model to include NPIs. So now let's think about how we can examine their effects and what the strength of those NPIs have on our epidemic. Okay, so suppose we're going to start with that transmission reducing NPI. So we're going to affect beta, and we're going to say we're going to replace beta with beta times by 1 minus r in our model. Okay, We're not going to specify whether this is reducing contact rates or reducing the probability of transmission per contact, because ultimately, as we saw here, those two things are multiplied together. So whether this 1 minus R factor is multiplying the C or the P, it doesn't matter. It's still going to just have the same effect on beta. So I already mentioned this already, but just to make sure it's clear, what does this R represent? Yep, strength of, not the virus, the NPI, yeah. Okay, and what does R is equal to 0 represent?
No NPIs.
Yep, no NPIs or no effect of those NPIs. So you could, in theory, have an NPI that is completely ineffective. And R is equal to 1. What does that represent? No contagious. So from like think of this from a public health perspective, if you're explaining this to someone and saying, okay, if R is equal to 1 in this model, that represents, yep.
Complete, I don't want to say immunity, but complete like protection from it. It works like 100%.
Yeah, so complete prevention of transmission. Or an NPI that is 100% effective. And in principle, this could have happened, right, in the pandemic. At least in theory, if right at the start of the pandemic back in 2020, 2019, if everyone in the world had stayed home for 2 weeks, then and had stayed completely isolated from every other human, obviously completely impractical, then this R would have been 100% effective and we would have prevented it, assuming that everyone would recover within those 2 weeks. It's a little bit more complicated because some people wouldn't, recover or die within those 2 weeks. But if there was a length of time for which everyone could stay at home, then it would get wiped out. Okay. So how about this next question here? How strong does an NPI that reduces transmission need to be to prevent an epidemic? In other words, what I'm asking is, when is this R0 less than 1, or you can think of it as your effective reproduction number, RE, being less than 1. Let's work through this one together. So we're talking about preventing an epidemic. So we're thinking about, and we're talking about this R0 being less than 1. In fact, this RE, we don't need that there, because everyone is susceptible, implied by that R0 there. So what that means in our model is that everyone is starting off as being initially susceptible, except for a very small number or one individual who's infected. And we want to see whether an epidemic is going to grow, R0 is greater than 1, or it's going to be less than 1. So how do we work out R0? Well, one way of doing that is to think about the dynamics of our I class early on. So we have S is approximately equal to 1. So the growth rate of our I class, and because we're having a small number of infected individuals, ideally just 1, and we're thinking about the rate at which infections are growing per infected individual, we can divide through by I. Okay, so what we're doing is we're going to get to take this di dt equation here, divide through by I, and set our S equal to 1. So early on in the epidemic, the growth is going to be approximately equal to beta. Remember, we're replacing this beta with beta times by 1 minus R, because that's the strength of our NPI. So we're going to have beta times by 1 minus R times by S. We don't have the I anymore because it's over this side here. And then we have a minus gamma, and again, the I is over this side here. And this S we're setting to be equal to 1, or very close to 1. So times by 1, or you can just leave it out. Okay, so this is our growth rate. And to prevent an epidemic, what do we need? for this growth rate here?
Less than 0.
To be less than 0, right? I've got it the other way around in the field notes, but we end up with the same thing. Okay, so for this to be less than 0, that will mean that our restrictions are strong enough that we're not getting an epidemic. The number of infections is going to be decreasing. So at this point, we've just got a bit of algebra. We need to rearrange this. Let's think about our effective reproduction number is just going to be equal to beta times by 1 minus r, divided by gamma. We need this to be less than 1. We don't really need to do this step here. This is just to clarify what our effective reproduction number is, okay? What we do need to do is just rearrange this to get r on its own. And that will tell us how strong those restrictions need to be based on this inequality here. In other words, for having this effective reproduction number less than 1, this effective reproduction number is also essentially the basic reproduction number here because we're not messing with immunity. But I'll leave it in this form here. We need beta times by 1 minus r over gamma to be less than 1. If we multiply both sides by gamma, divide by beta, and then add r and switch the sides around. In other words, we're just getting r on its own here. We're going to get r has to be greater than 1 minus gamma over beta. In other words, 1 minus 1 over r naught. This model, r naught is beta over gamma. Does anyone recognize the form of this in the last lecture? It's the same threshold that we had for our vaccination threshold. It shouldn't be too surprising, right? Because this beta SI term that we have up here, we talked about vaccinating individuals and reducing this S term by a certain factor, right? And then we ended up with a vaccination threshold of 1 minus 1 over r naught. But this term here is just multiplied by this transmission rate. So if we reduce this transmission rate by a factor of 1 minus 1 over r naught, or we reduce the number of individuals available by a factor of 1 minus 1 over r naught, because we're just multiplying these two things together, it's kind of like this thing over here, this 1 minus r. It doesn't matter which term you're affecting, you still need to have the same strength effect, okay? So that's why this threshold is the same, is because we're just multiplying that transmissibility, the transmission rate, and the proportion of the population that is susceptible. If you remove one of those or reduce one of those by a certain amount, it's the same as reducing the other thing by the same amount, okay? That's why we get the same threshold here. One thing this will do that's different, though, is reducing the final size of our epidemic. So if you remember, I'm changing the notation a little bit here just to avoid confusion with R's. Remember a few lectures ago, we talked about the final size of an epidemic, which we called W sub F. I say I'm using the notation from that lecture just to draw the parallels with that lecture there. And we found that the solution, or the final size of an epidemic, is given implicitly by this equation here. 1 minus WF is equal to e to the minus R naught WF. Does anyone remember that? Does that look familiar, or have you forgotten what this looks like? Somewhat familiar. Okay. So we solved this by sketching the line 1 minus WF as WF varies, and likewise sketching this curve here, seeing where they intersect. That will give you the final size of the epidemic. There is no analytic solution to this. We can't just get WF is equal to something. You have to solve it numerically or geometrically. Okay. So in our model, if we think about, and the reason I left it in terms of this effective reproduction number above, we're now going to have the final size of our epidemic is going to have RE replacing R naught. This is why, even though we're not messing around with immunity at all here, I've left this in terms of this effective reproduction number, just to make it clear what we're talking about here. So here, this R0 would have been beta over gamma, and our RE is going to effectively be beta times by 1 minus R over gamma. So what does that do? And this is only true, obviously, if R is less than 1 minus 1 over R0. Why is this condition here? If my restrictions are less than 1 minus 1 over R0, the final size of our epidemic is going to be this. Why have I stipulated that? What happens if R is greater than this? We've just gone through it on this slide here. If R is greater than 1 minus 1 over R0, what happens?
We prevent an epidemic.
Okay, so if we prevent an epidemic, then we're not going to have a final size of that epidemic. Okay, so we're only thinking about when our restrictions are low enough. What we're saying here is that the disease is suppressed, so we have fewer number of cases compared to what happens if we didn't have any restrictions, but we still get an epidemic. It's just smaller than it would have been. So what does this look like? Let's sketch something over here. You think about these two cases, with and without restrictions. So here we're varying the final size of our epidemic. And this is the line in red, 1 minus WF. And then our original curve of e to the minus R0 WF maybe looks something like this. And this intersection between the green and the red lines would give me the final size. So let's call this, say, W0, final size of our epidemic with no interventions. If we decrease RE through these restrictions, so through this term here, if we increase R, we're going to be decreasing RE. Because this is a negative exponential, our curve is now going to look something, say, like this. This is e to the minus RE WF. And so we've shifted our intersection up and to the left. Let's call this W1. So we see the final size of our epidemic is going to be reduced. If you increase R enough so that R is greater than 1 minus 1 over R0, this purple line will keep shifting up until there's no intersection, or rather the only intersection is at 0. Yeah. Sorry, 1.
The y-axis, the R.
So the y-axis is just the value of whatever these equations are here. Just the right-hand side. Oh, sorry, this would be the left-hand side, the right-hand side. Okay. So this value up here is just 1, where it meets the y-axis. Okay. So we can see that even if we don't manage to prevent an epidemic, what we're doing is we're shifting this intersection up, and therefore we're reducing the final size. One of the interesting things as well, if you were to simulate this, there is some code online from previous lectures where we looked at SIR models. If you just reduce your transmission rate, so suppose this is time, we're going to do our number of infections. Suppose this is my epidemic that I would get something like that maybe. That's with my standard beta. If we have restrictions, we end up getting something that looks more like this, say. So this would be my beta times by 1 minus R. So there are two effects of these restrictions. What are they? Yep, so it does reduce the overall size of the epidemic. We know that already. So, in fact, there are three effects. So one of them is reducing the final size of the epidemic. In other words, if you integrate under this curve, you would be able to get, if you switch this around to be incidence, you would be able to work out the total number of infections is based on the number of individuals infected. And so the area under this curve, if this was incidence, at the moment this is prevalence, which is slightly different, but the same idea applies that ultimately there is more area under this red curve than there would be under the green curve. So that gives you something related to the final size of the epidemic. What else is it doing to these curves, though? How would you describe the red curve compared to the green curve as like key characteristics? Yeah?
The red curve is much higher peak, and the green curve has a much longer lasting.
Yeah. So, in fact, we could even potentially break these down further. There's a higher peak when we don't have restrictions. It also peaks earlier. The green one, we have a more drawn out epidemic, but we have a lower peak and the peak is later. So there are multiple effects here of having these restrictions. And this is an argument to having restrictions in, even if they are not going to completely prevent an epidemic, right? If you think about this as the start of your pandemic, if you don't do anything, you get hospitals overwhelmed in this scenario, right? Potentially. You have a very high peak, systems get strained. Also, it doesn't give you much time to prepare. It doesn't give you much time to potentially develop new treatments. So the longer you can push this peak into the future, generally the better it is. It will mean that you have this, in this case here, you've got restrictions in place for a much longer time. Here you've got no restrictions, but more restrictions mean that those restrictions have to be in place potentially for longer, but you also have a much lower peak. So it drags things out, but it makes things overall better. Okay. Great. Let's move on to think about a different type of NPI. So we talked about effects on beta or effects on gamma. And one of those effects on gamma was having some sort of diagnostic testing. So when I'm saying effects on gamma, obviously this is just here I've separated it out, but I could combine this. If you thought of gamma as being your total removal rate from this class, you could combine this into here, but just by replacing this as one parameter. You could have gamma plus tau, right? And just replace gamma prime is equal to gamma plus tau. Okay, so we're thinking about gamma as representing a removal rate, okay? Regardless of where those individuals go. So let's think about diagnostic testing. It doesn't affect transmissibility. It's going to affect that removal rate. And we're going to separate it out. So it's not subsumed into gamma. We'll give it a different parameter. So what we're going to do is suppose we randomly administer in this population a perfectly accurate, so it's always correct, whether someone's infected or not, diagnostic test. And we're doing this at a per capita rate tau. When they take the diagnostic test, they're immediately moved to a temporary quarantine. So we need another class like we had before. And this fully prevents further transmission. So they're not causing any infections. And then they remain in quarantine for an average duration of 1/d, after which they're classed as being perfectly immune and they are no longer infected. So what I want you guys to do is to sketch a transfer diagram, so a schematic of what this model looks like, and then write down what I've called an SIQR model. We have this additional class here, which is our quarantine class. We're going to do this without any demography, just like our SIR model earlier. We're just modifying that one. Q is the proportion of the population that is temporarily quarantined. So using this information here, modify the model, draw a transfer diagram and write down our equations. Okay? Does anyone not know what they're doing? Okay, I'll come around and have. It's like you've got something down, so I'll go through this. Okay, so we're just modifying the model we had before. So we had SIQR and R. Separate these out a little bit more. And we've got this new class Q, which is individuals who are in temporary quarantine. Now, you don't have to always sketch a transfer diagram, unless I was to say, ask you for one in an exam. But doing this can help you visualize the flow between these things. If it helps you to understand this type of, let's go all the way back up here to these equations. If it helps you to understand what's going on, think of these as being different buckets. And the buckets contain a certain amount of liquid, and there are pipes connecting those buckets, and the pipes can only, say, flow in one direction. Those pipes would have to have pumps in them to account for things, but it's you can think about the proportion of individuals in each class as the amount of liquid in that bucket, say. Okay, so just think about movement between these as being things like flow. So before we had infections occurring at a per capita rate beta I, sometimes you'll see these written not as their per capita rates. It might someone write this as beta SI and everything as the total flow. That is fine, as long as you're consistent, okay? It would be wrong for me to do beta I and then say, oh, I won't do that Q yet, I'll do the R. It'd be wrong for me to do beta I and gamma I, because here I'd be doing per capita rates and here I would be doing total rates, okay? So it doesn't matter which you do, as long as you're being consistent. Here I'm doing per capita rates. So that was the original model we had. Now we've got quarantining. We're told that we're administering a perfectly accurate test to everyone at a rate tau. Note that I don't actually specify here. I say I'm randomly administering this to everyone in the population. So I'm also administering this to individuals in the S and the R class, and in the Q class potentially as well, right? But it doesn't matter because they get a negative test and nothing happens with their negative test, so we don't have any arrows corresponding to that. Okay, so they move into the Q class. And then we're told that they remain in quarantine for an average duration of 1/d. Now remember, when we're talking about these models, we're talking about exponentially distributed times. And this exponentially distributed time has an average duration of 1/d here. That means that the rate is just going to be d. Okay. The rate of going from Q to R is d. That's our transfer diagram. And then our set of ODEs, well, we've got the same DSDT as before, minus beta SI. Our DIDT is now going to be beta SI minus gamma I minus tau I. We've got a new equation dQ dt, which is going to be tau I minus dQ. And then dr dt is going to be gamma I plus dQ. So if you were to do a transfer diagram and write down your equations, good check to go back and make sure that this perfectly matches what you've got up here. An arrow out represents a minus sign. So look at all of the arrows going up this S box, just this one here. In this case, the DIDT box, what are the arrows going out? They must have a negative sign here with a minus gamma and a minus tau. Everything with a positive sign is an arrow coming in. So for example, this DIDT, there are two arrows coming in, one from I, one from Q, and it rates gamma and D respectively, okay? So a good way of checking that your schematic matches your equations is to just take a moment to go back and check. Okay, so what does diagnostic testing do to our average infectious period? Can anyone tell me what the average infectious period is now? Or maybe let's start off, what was the average infectious period if there's no testing? Yep. Okay, so we had 1/gamma before. What's our average infectious period now?
Gamma minus 1/d.
Not 1/d. When I'm saying it, I should be clear as well. Infectious period, I'm just thinking about this class here. Okay, so I'm classing because I said infectious rather than infected, right? So the average infected period is not any different, presumably. I mean, it's not entirely captured by this model here because we're just saying individuals stay in the quarantine for D and then they're just classed as this immune class. But the time that they're essentially going around infecting other people and free to infect other people is entirely determined by this equation here. So before we had 1 over gamma as our average infectious period, what's it going to be now?
1 over minus gamma minus D.
Not minus, because if it was that, then it would be a negative duration.
1 over gamma plus tau.
Yes, okay. It's 1 over gamma plus tau. So to work out an average infectious period, you basically just look at what is the per capita loss rate from this DI/dt equation. So if they're being lost, we could write this here as minus gamma plus tau, this bit here, which is minus gamma plus tau times by I. And therefore, the loss term, per capita loss term is gamma plus tau. The average infectious period is going to be 1 over that. So what is testing doing to the average infectious period in this particular model? If we start testing more and more and more, what's it going to do?
It's gonna decrease.
Yeah. So testing reduces the average infectious period. That makes sense, right? We're testing and then quarantining individuals. We're classing the infectious period as the time that they spend going around able to infect other individuals. If we're testing them and then quarantining them, the more we test, the more likely we are to pick them up earlier in their infection and quarantine them earlier in their infection. So the less time on average an individual is going to be able to spend infectious, in other words, going around infecting other people. Okay, just like we did before with the transmission, reducing NPI, we can calculate the rate at which we must administer these diagnostic tests and quarantine people, because obviously testing by itself doesn't do anything. We need to have some action. How fast in this model must we administer those diagnostic tests to prevent an epidemic? So again, we're going to start off by thinking about what happens when almost everyone is susceptible. S is approximately equal to 1. We have. Anyone tell me how I'm going to work out this rate? What do I need to do? What's the first step I need to look at? Yeah, Mark?
DI/dt less than 0.
Yeah. In fact, we can look at its per capita rate, right? So we can think about the per capita growth rate of my infectious class, which in this model is just going to be beta minus gamma minus tau. In other words, just this equation here divided by I, and seeing when this is less than 0. I say we have, this should really say we need. We need this to prevent an epidemic. Again, we don't need this line here, but we can work out our basic reproduction number, which is effectively what we're doing here, as beta over gamma plus tau. Remember, this averaging, this basic reproduction number is just the rate at which one individual who's infected produces new infections, which is beta, multiplied by the average duration of infection, which we just worked out as 1 over gamma plus tau. Okay, everything that's coming in divided by everything that's going out. We need this here to be less than 1. We don't need that line in, but it's just for completeness, just to illustrate what's going on with our basic reproduction number. This is just a simple inequality here. We can get this in terms of tau. Okay, we just need tau, our testing rate, to be greater than beta minus gamma. In other words, the difference between the rate at which new infections are being produced early on and the rate at which those infections are being lost. As long as we can tip this balance with a testing rate that is greater than this difference, we're going to prevent an epidemic. Any questions? Yes.
So the reason we don't get like R1 minus 1 over R0 for this one is because we're not changing the actual rate at which infections happen, we're changing the rate at which they.
Yes, exactly. Yeah. So this is a different type of threshold. This is also, this is not a universal finding in the same way that 1 minus 1 over R0 crops up very often, because it is related to the peak of an epidemic. This here is kind of particular in the way in which we said tests are administered in this model. There are different ways in which you might administer tests. You might say test everyone at the first sign in which they get symptoms, and maybe that test is not 100% effective, in which case it will adjust this threshold. You might repeatedly test individuals. You might just give them one test. Your quarantining class might not be 100% effective at preventing transmission. People might stay at home, but they might still infect their family members, say. Or they might occasionally, go to the grocery store. So this is just one particular example, and it's important to remember that different scenarios involving testing would give you different thresholds. Okay. In theory, different vaccination scenarios would also give you slightly different thresholds, but that 1 minus 1 over R0 is something that's a bit more universal than this particular result here. Okay. Okay, any other questions? Yeah, Scott?
So would this affect the final sizing?
Yes, good question. So it's changed your R0, it's changed it in a different way, but in just the same way, if we think of your R0 when tau is equal to 0, so when you've got no testing, if you increase tau, then your R0 is going to get decreased. And that will have a similar effect to here, right? You can think of that new R0 as being like an effective reproduction number, and therefore it would shift it up just like this. It would do it, there's no sort of direct comparison between the strength of transmission reduction NPIs and the rate of testing, because one's a number, one is a rate, but they would have qualitatively a similar effect. The more restrictive you are in transmission, or the more tests you administer, or the faster you administer them, they would both shift this up. Yeah. Any other questions?
We didn't include a death rate.
We didn't include a death rate. You're very right. So I did mention this at the start, that we're not including death rates in these models for simplicity. But an example here, if we had a death rate here, often it's referred to as alpha, it would affect this class here. Okay. One of the reasons we're not doing that is because we're trying to keep the population size constant in these models, just because it makes the analysis more simple. I might include it in a practice problem, or possibly even an exam question, you never know. I might include disease-associated mortality and step you through how we would include that. But it does cause slight issues because it changes the population size. You can almost think of these as being labels for individuals. And here the total number of individuals isn't changing, it's just their label that's changing, their disease status. Whereas here, we're starting to remove individuals. So that changes things.
Then it will also affect VQ,
Yes, they could also, in this, yeah, if we were having a quarantine class, they could die from that as well. Yeah, so there would be a minus alpha Q, say, or it could even be a different, because maybe they're getting treatment now that they've had a test and they know that they're infected. But good question, yeah. Okay, that's it for today, guys. I will see you on Friday. I think we're going to start moving on to look at evolution. I think, if I remember rightly, there's only 3 more lectures of new material, and then a quiz, and then a review at the end. I did mention this on Monday, but for those that weren't here, the review on December 4th is our final class. I'm not going to be able to review everything from the entire course, but what I'd like is if you could drop me an email, maybe ideally by next Wednesday, or at the latest by the end of next week, because I'll be putting the notes together, to tell me things that you would like me to go through in more detail. Okay, so I can structure it myself, but it's more helpful if I know what you guys want me to focus on. So drop me an email, let me know what you'd like me to go through in that review session. Have a good week.
Thank you.